Hello, everyone. This is the lecture for section 4.1, exponential functions. So this is going to be our transition in the second third of our course. We are going to move on to exponential functions first, and then logarithmic functions, which are sort of the inverse of the exponential functions. And after that is going to be the beginning of trig. That's what's coming up in the next couple weeks. If you recall from the last couple sections, right? So section one, chapter one, dealt with just sort of notation and how we write math down in general, right? Chapter two was lines. Chapter three was polynomials, things that are like x to the 8th, x to the 15th, stuff like that, right? Now we moved on to our new set of functions, exponential functions. Okay, so first of all, what I want to do is just define what an exponentiation is, what it is, what it means to be an exponential function. First of all, okay. So if you guys recall, if you guys remember way back from kindergarten, right? Um, uh, just how multiplication, right, is repeated addition, right? So if we write this, right, 3 times 5, that is the same thing as me saying 3 plus 3 plus 3 plus 3 plus 3. I'm adding, whoops, plus 3. I am adding 3 to itself, right, 5 times, right? And this should be 15. And then the other way that we can write it, right, is 5 plus 5 plus 5. That was equivalent, right? That we can add 5 to itself 3 times. This is also still 15, right? Okay. Exponentiation is the exact same thing, with the only difference is that there's no multiple way of doing it, right? There's no multiple way, like for example, multiplication had the two ways of representing the same thing, right? For exponentiation, there isn't, okay? We only write it one way. So if we say, actually, let me do it this way. 3 to the 5th, right? That is repeated multiplication of 3 5 times. So 3 times 3 times 3 times 3 times 3. Okay? Which is different, right? These are not the same thing as 5 to the 3rd. Okay? This is 5 times 5 times 5. Okay? So 3 to the 5th. So 3 times 3 is 9 times 3 is 27, times 3 is 81, and then times 3 again, I believe, is 243. And then 5 cubed, that's going to be 5 times 5, that's 25, times another 5, that's 125. Okay, so this is what we're going to get into right now. We're going to get into exponentiation, repeated multiplication in this case. Okay, all right. So now, there's a bunch of rules that exponentiation has. That is all of these. So let me cover them really quick. Okay. But the practice, the warm up that I'm going to have you guys do, we can do them all in class. This might take an hour in class, maybe even longer. Okay. I want everybody to be comfortable with being able to use all of these rules on your own. Okay. So let me cover them first. Okay. So the first one is the product rule for exponents. Okay. So that basically says, okay, if the bases are the same, okay, if those a's are the same, right, and you're multiplying the two things together, right, then that's equivalent to just adding the exponents together. Okay. Okay. Next one down. Let's say you have an a times b, and you grab all of a times b and do it to the nth power, okay? This is the multiplicative distributive rule. So basically what we're saying is this n power sort of basically hits both the a and b separately, and you get left with this, an times b to the n. So the n got distributed to both of those. Okay, moving on. Suppose you had the same base, different exponents, okay, but you are dividing them. okay, then that means you can subtract the top minus the bottom, okay? Okay. Likewise, just like multiplication had it, there is one for the division. There's a division or a quotient distributive property, okay? Basically saying that that power n gets to distribute to the top and to the bottom, okay? So you get this as an outcome, an divided by bn. Okay. Next one. That one. Okay. Suppose you had a to the n to the m. So you had something to a power to another power. Okay. You can simplify by multiplying the powers. As so. So basically grab those two values, whatever they are, multiply them. Okay. Those are just to reduce or distribute exponents, right? There are three more down here, okay, that I'm still going to explain, but these are much more used for rewriting an expression rather than outright computing something, okay? So the first one is the fractional powers rule, right? So if you have something that's m to the nth root of a to the n. So suppose, right, you have a to the n inside, right? And then you're going to take the mth root. Hopefully you guys remember you can take the fourth root, fifth root, the square root, right? Then you can rewrite it as a fractional power. You can rewrite it as a fractional power, okay? Next one. Those two right there. So whenever you have a negative exponent, you can do 1 over the positive exponent. That's just the negative powers rule. Like I said, these two are much more to rewrite stuff rather than to solve anything, okay? The last one, we need it just so that the rules make sense and we don't break anything, basically. A to the 0 power is equal to 1. A can be whatever it wants. So anything to the 0 power is always equal to 1. Okay? All right, like I said, this is going to take us a little while. I'll have you guys do these warm-up problems in class, and I'm probably going to give you guys a good hour to get these right. Okay? All right, so now let's get into what exponential functions really look like. Okay? An exponential function looks like this. Okay, there's one thing in this definition that I got from the book. I'll give you guys that. There's one thing in this definition that is not mentioned, okay, that your b has to be positive. Some real wacko stuff happen if you make b negative. If you make b negative, it can still happen, but it's going to be real wacko, real crazy. Okay, so, and what I'm going to do, I think I've done this maybe once before. I will defer to your course of study when b will be negative. Okay, basically saying if you see this being negative, you're probably doing some high-level physics, high-level chemistry, high-level math that we really don't need to worry about right now. Okay, so pushing that off. All right, so now let me show you guys what an exponential graph looks like in comparison to something that we already know. Okay, so in this one, right, we have two functions. We have f of x being 2 to the x and g of x being 2 times x. Okay, so f of x is the one that we have displaying exponential growth, as opposed to something like g of x that is linear growth. Okay, so from the table, hopefully you guys see the table here, right? The graph only gives us maybe up to 3, maybe x equal 4, maybe up to here, right? So the rest of this gives us the rest of the graphs, right? So when we plug in 0, that's going to be 1. When we plug in 1, that's going to be 2, 4, 8, 16, 32, 64, so on and so forth. Okay? All right. Now, what I do want to explain here is this. If you guys remember, I'm going to do this in two different colors, right? The linear function, we had a phrase for that. It was a constant amount change. Okay, and the way that you would spot this, right, is if we went from here to here, notice that our x's are increasing by 1 every time, right? Our x's are increasing by 1 every time, right? You guys see that? Okay, so from here to the next point, we added 2. From here to the next point, we added 2, added 2, add 2, add 2, add 2. Hopefully you guys see that, right? This is where we got the phrase constant amount change, right? Okay. What I want everyone to see now is that for this one, what we're going to have is called constant percent change. Okay. And the way that we do this, okay, is this way. Hopefully you guys see what's going on now, right? Our x's are still increasing by 1, right? So it's still going 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. But what's happening with our y values is that we are multiplying them by 2 every time. So 1 times 2 is my 2. 2 times 2 is my 4. 4 times 2 is my 8. 8 times 2 is my 16, and so on and so on. Okay? What we say here, right, is if you guys see that we're multiplying them by 2, right? The way that we have that sound or relate that back to our constant percent change is that it's growing by 100% every time. That's where our times 2 comes from. Okay? Okay. So now, let me scroll down a little bit. Now that we have all the graphs there, okay, I've got to give you guys all of these things. So the domain, the range, the horizontal asymptotes, some behaviors of our f of x in this case, some behaviors of the x-intercepts and the y-intercept. Okay, so the domain, hopefully you guys see, for 2 to the x, right? The domain is negative infinity to infinity all the time. Okay, the range. Hopefully you guys see that this green line, right? I'm going to highlight it really quick. This green line right here sort of looks like it's hugging that x-intercept or that x-axis, right? So that gives us 2 things here, right? 3 things actually. First of all, let me start with this one, that the f of x, the exponential graph, right, has no x-intercepts. Okay? It's also going to always be positive. Okay? And hopefully you guys see, I'm going to do it in red since we're used to the red marker being an asymptote. It's going to have an asymptote at the y-axis, or sorry, at the x-axis. Okay? So the horizontal asymptote is going to be y is equal to 0 all the time. Okay? Which means our range is going to be 0 to infinite. It's going to get really down close to my x-axis, but it'll never cross it. Okay? The last thing that I have to show you is the y-intercept. Always going to be this point right here. 0, 1. We'll get to where it changes in a second, in a little bit. And I'm talking about this point right here. This point right here is going to be 0, 1. My y-intercept. Okay? Okay, you guys are probably asking yourself, why the 1? Why? Where'd it come from? When you write out 2 to the x, we are sort of assuming that we're writing this down. 1 times 2 to the x. That's the 1. That is the 1 for the y-intercept. Okay, so whenever we write these things out, right, the b to the x is going to be our exponential function. Okay, and my a, let me actually do these correctly. Boom. And then my a is going to be my y-intercept, or my initial value. Okay. All right, let's keep going. Which one of these are not exponential functions? I'll give you this one. This one is not. Unfortunately, this one is not. Let me actually not cross it out there. Let me cross it out down here. Yeah. So the key for an exponential function now is that the exponent is now in the power. Does that make sense? All the other ones do it. You guys see that that one has a power, that one has a power, that one has a power. And the exponent, right? The variable is in the power. So this one's good, this one's good. Okay. Let's get to, now that we've identified, right? Let's get to solving stuff out and applying it to certain things, yeah? All right, so first of all, evaluation happens exactly how we did the evaluation for everything else. So if I wanted to do f of 2 and f of negative 2, right? I've got my function, right? 5, 3 to the 2 plus 1. 5, 3 cubed. So remember your order of operations. Parentheses, exponents come next. So we have to do the exponent first. Okay, in this case, we have to do this bit first, the 3 cubed. And that is going to be 5 times 27. And that is 135. Okay, f of negative 2. 5, 3, minus 2 plus 1. 5, 3. The minus 2 plus 1, that's going to be a minus 1 left over. Okay, so this is the importance of something from our exponent rules from the beginning of the section, right? This can be rewritten as 5 times 1/3. And this reduces now to 5 over 3. Boom. So you guys see that the evaluation portion is not any different than what you know from before. Okay? Okay. Now let's start applying this stuff to stuff. Yeah? So the first thing I'm going to cover is exponential growth and decay as a constant percent change. So you remember that constant percent change definition or the characteristic for an exponential function that I just covered above, right? That's the easiest thing to start applying toward a bunch of stuff, not only just sciencey stuff, but finance, the softer sciences, so sociology, psychology, pops up real heavy already in biology, in chemistry, a lot. Okay, so let me cover it really quick. Okay, this should look familiar. That is the form of an exponential function, right? We know that the a is supposed to be sort of the initial amount, right? That's where it's actually coming from, right? And b is what we call our growth factor, okay? Or our growth multiplier per unit x, okay? There is something that we have to do for that b value, okay? So in our scenarios and the things that we're going to be seeing, okay? If you have a scenario that is providing a form of growth that you know it's growing, right? Then that B value is going to be 1 plus some R, where R is going to be the rate of growth, okay? If you have a scenario where something is decaying, something is going away exponentially, right? Then your B is going to be 1 minus R, okay? And R is going to be the rate of decay, okay? These are going to be semi-difficult to spot, okay? But I think once you spot one of them, right, and you do one of these, the process is sort of self-explanatory. So let me go ahead and do example 4 here, okay? So let me read it out. The population of India is about 1.25 billion people in the year 2013, okay? What is with an annual growth rate of about 1.2%. So first of all, what I'm going to do is provide an equation that models the situation, with t being the time since 2013 and p of t being the population at t years, okay? And then after that, I'm going to find out, according to my model, what will the population be of India, right, in 2031. Okay, so notice what this thing says, okay? It's an annual growth rate of 1.2%. Okay. So I'm going to do this. I'm going to say my R is 1.2%. Okay. I need to convert this to decimal. Okay. And the way that we do that, I'm going to do it over here, 1.2%. Okay. I'm going to grab this decimal. I'm going to go 1, 2 over. So this is the same thing as 0.012. This is me converting a percent into a decimal, if you guys remember that from kindergarten, right? So 0.012, that is my decimal value, okay? So then that makes my B, since I have a growth, notice how it says it's a growth, right? That means I'm going to be using my first one. I'm going to be using the 1 plus R. Got it? So it's going to be 1 plus 0.012, the R that I found right here. And that's going to be 1.012. Okay. Now, my P of t, my function itself, okay, my initial value, 1.25 times 1.012 to the t power. This right here is my equation. This is my model for the population of India. Okay, now I need to find out the population when it is 2031. My initial year for this data, for the numbers that have been given, is 2013. So if you take 2013 and see how many years it is from 2013 to 2031, hopefully you guys see that's 18 years. So I'm looking for P of 18. So this is going to be 1.25, 1.012 to the 18th power, and that is 1.55. Okay, so in 2031, right? Whoops, India. Okay, dunzos. In a way, right? A lot more of these problems can be done on paper than from the stuff that we did back in the day when we had to do polynomials and lines, right? We needed tons of space to find the equation of a line. We needed tons of space to figure out, the vertex or this or that, right? In this case, look at my answer real quick. Okay, I've got a quick check for you guys to try. Okay, we'll try, like I said, we'll try these in class. You don't gotta do them now. Okay. Okay, moving on. Finding equations for exponential functions. This can be done varying ways. Okay. There is no right or wrong way to do it, but hopefully you guys see that it's sort of like how to identify that something's sort of exponential. You guys see how it's curving upwards, right? And it's not in a line fashion. So it's not one of these. It's not whoosh, right? You might be able to argue a polynomial, like a quadratic. You guys remember an x squared or an x cubed? You could, right? But for the sake of what we're learning here, right? Let's gonna go ahead and assume that that we're messing with exponential functions, right? Okay, here we go. How do we solve this? So here's some data for iPhones sold from 2012. So in 2012, let me see, where's 2012? There we go. In 2008, sorry, in 2008, there was 11.63, okay? But by 2012, we have 125.05. We need to find an equation that models this kind of growth, okay? So like I said, let's assume that it's gonna be an exponential function, right? And I'm gonna go ahead and start doing this thing. You guys remember the multiplying, right? That we to get from one to the other, from one to the other, from one to the other, we multiplied by 2, right? So I'm going to try to find out what I need to multiply each one of these by to get something closely related. Got it? So, for example, okay, if I grab, I'm going to do it over here, 11.63 and then divided by 1.39. That is going to be I'm looking at this from my notes. There we go. That is going to be 8.36. Okay, we'll do it again, but this time around with these two. So 20.73 divided by 11.63. Okay, and that's going to be 1.63. No, sorry, 78. Just going to use 2 decimal values for now. Okay, if I do that every single step, I get these values: 1.93, 1.81, 1.73, 1.2, 1.13, and then our last one went up way up here, 1.36. Okay. Okay. If you grab, right, the average, and these are going to be all my B's, all of these. I'm going to highlight each one of these. Okay. If you grab all of these B values and average them, right? You're going to get 1.56. Got it? So then what we can now do is this. Our N of T, our number of phones sold over time T is equivalent to 11.63, 1.56 to the T. We are done. Like I said, there's no real right way to do this. There's even there's some statistics that's actually focused around this kind of function. Okay. However you can figure it out, more power to you. Does that make sense? Hopefully it makes sense. I know this feels a little wishy-washy, right? But yeah, this is how it works. This is how it works in real life. Okay. Okay. Moving on. This hopefully you guys remember. Uh, Compound interest. This is the beginning of, for all of you that are taking pre-calc to get into finance, to get into economics, this is the very first thing that you're going to learn for those fields. Okay. Compound interest is this formula right here. Okay. It doesn't look like it, but it is an A times B to the T. Sort of that P is going to be my A. All of this, including my N, is going to be, including my N, is going to be my B. And then the T is out there floating around. Okay. So let me get to the anatomy real quick. A is the account value after T years. T is measured in years. So make sure you take a note of that. Okay. The P is the starting amount of the account, however much was in there. It's often called the principal value or the principal amount, right? Or more generally, the present value of the account. Okay. R is considered the annual percentage rate, your APR. Okay. And you have to express it as a decimal. Okay. Just like I did before, I had to convert the percentage into a decimal. You got to do that here too. Okay. And N is the number of compounding periods per 1 year. Okay. Some common ones. I'll write that down. Semi-annually, that is 2 times, right? Monthly, that is 12 times, right? Quarterly, that is 4 times, right? Daily, that is 365 times. 65. Weekly, that is 52 times. There are 52 weeks in a year. Okay? So depending on the explanation, that's the one that you're going to use. Okay? So let me run through an example really quick. Okay? Suppose we had 3 grand, okay, and we invested it into an account paying 3% interest compounded quarterly. Okay? What is the equation of the investment account? And then how much will we have in 10 years? So we first have to construct the equation. Okay, so hopefully you guys already see it, right? So I'm going to list my stuff. My P is going to be my 3,000, right? My R is going to be the 3%, right? But I have to convert it into decimal, so 0.03. N is going to be, what's my N? Quarterly, so 4. Okay, off to the races. So P of T, 3,000. 1 plus 0.03 divided by 4 to the 4t. Okay, and if you clean this up anymore, sometimes you might want to, 1.0075 to the 4t. We are done in terms of our equation. Okay, now, how much will this thing have in 10 years, right? P of 10 is what we're looking for. 3,000. 1.0075 to the 4 times 10, 3,000, 1.0075 to the 40, 4045.04 should be your value. Okay, you can compute this using Desmos. Okay, play around with it. Try it out. All right. What comes up next? Quick checks. Have you guys do some quick checks with it. Okay. Last thing we got to cover. at least for this section. The number E. So I gave, in the previous section up above, I gave a couple of values for this n that's right here, for this n that's right there, for that n that's in the exponent, okay? I gave you guys a couple of values, right? So daily was 365, weekly was 52, semi-annually was 2 times, right? So what happens if we just do that every moment? Hopefully that makes sense, right? So instead of just doing it every day or every week or every month, right? What happens if we let every moment be a moment where we compound an interest, right? What happens? That is where this number, the number E comes from. Bam, that thing, okay? It turns out, in terms of finance, right, that's how you explain it, right? And it's easy to think that that's the only time it'll happen, but it doesn't. It actually happens a lot in the natural sciences. Certain things, certain plants, grow revolving around this exact expression right here. Okay? If we need a value for it, there is a value for it. 2.71828 and change. So it keeps going, right? That is the numerical expression for it, okay? So, in Desmos, actually, let me open up Desmos so I can give you guys the example for it. Come on, where are you? There we go. Okay. Whoa. Okay. In Desmos, we can compute this stuff. And if you give it E, it'll give you the decimal value for it, right? And you can start computing stuff with it. So let's say I wanted E to the 3.14, not pi, just 3.14. Okay. There it is. E to the 3.14 is about 23.10386 dot 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 dot. Okay. So Desmos, like I said, this is why I love Desmos so much. Desmos is a pretty darn good calculator in its own right. Okay. Play around with it. Okay. Let's keep moving on. We haven't gotten to the good stuff yet. This is the real good stuff. Okay. When we start talking about exponential growth and decay. Okay. This formula should look pretty familiar. It's still an A, B to the T. So my A is still A. This thing is my B, and then my T is still floating out there in the exponent, right? Same thing here. My P here is my A. My E to the R is my B, and then my T is the thing that's floating out there. Okay? When you have things that look like this, we are calling them continuous growth and decay. So this right here, the continuous, would be your trigger word that tells you that you need to use these in particular. Okay, so let me go through the anatomy for these functions real quick. Okay, so in this case, the A is still my initial value. The R is the continuous growth rate per unit time. So like I said, whenever you see that word continuous, that's going to be your sort of like your trigger word to say like, oh, I need these in particular. I need these functions in particular. Okay. If R is greater than 0, then you have a continuous growth. If R is less than 0, you have a continuous decay. So this one's a little bit more straightforward. In the previous one, remember we had the A, B to the T, right? We couldn't just plug in B. We had to do something before we plugged in the B. We had to do either the 1 plus for growth or the 1 minus for decay. In this case, the R that you get is the R that you get. If it's positive, it's growing. If it's negative, it's decaying. That's simple. Okay? For business applications, I don't know why the book separated it away. It's the same thing. It's the exact same thing. P is considered our principal. amount or our initial investment. Okay, the R is the growth or the interest rate per unit time, right? The R is still whatever it's supposed to be, right? And it has the same rules as the one up above. If R is positive, it is growing. If R is negative, it's decaying. Okay, and then T is the time period, however long you wanted to invest your money in. Okay, okay, and for both of these, right? For both of these, the T can be in any measure of time you want. It can be in years, it can be in days, it can be in months, it can be in hours. Okay, so just keep in mind of that when you are trying to do some stuff with it. Okay, okay. So let me give you guys an example of what I'm talking about here. Yeah. Look, suppose we have a radioactive substance and it has a continuous rate of decay of 1.5% each day. Okay. If we initially have 150 grams of the substance, how much will we have after 120 days? Okay, so this happens a lot. Notice I'm talking about a radioactive substance. Once you get into radioactive physics or the higher ends of chemistry, right, you start talking about radioactive stuff. Okay, and these things do decay. So you have an amount of it, right? And after a certain amount, because of the properties of radioactive substances, they decay into something smaller. And then they keep decaying into something smaller and more and more and more. Okay? So, how do we create our function, right? And how do we solve our functions, right? How do we solve for these situations? Okay? So, we're going to go start the same as we did before, right? My P, right, or my initial amount is going to be the 150 grams. Okay. My rate is 1.5 decay, percent decay. So then that means that I'm going to have 0.015, but negative. Since this is saying that it is decaying, I know that that 1.5% has to be negative. And we are essentially done. A of t is 150, e to the r, negative 0.015 t. We have our function. We are done. Okay. Well, actually, let me write this a little nicer, huh? There we go. We are done. This is our function right here. Boom. Okay, now the question is asking, how much will we have left after 120 days? That is the same thing as doing A of 120, 150, e to the negative 0.015 to the 120. Okay, here we go. Let me bring Desmos back up. 150 times E. You guys see how it automatically did its thing. Negative 0.015 times 120. Why'd it go away? Maybe I should do a double. There we go. There we go. 24.795 grams. There we go. So now, let me summarize what we just did, right? We know that this thing, this substance, radioactive substance, was decaying, right? We started out with 150 grams of it, and after 120 days, we get left with 24.795 grams, okay? So after 120 days, we are left with 24.795 grams. Some of you guys have had science classes before, and the word sig figs might scare you. This is a math class. I don't particularly care about sig figs. So give me as many decimals as you want as a nice general sort of point. Two decimal values after the decimal point is enough for me. So I could have just done 24.79. That would be fine. If you want to give me more, it's fine, but it's superfluous. I'm not going to look at much more than the first two. Okay. All right. And I believe that is that. After that is lecture questions. If you have any questions on the stuff that was just covered, ask me during class or come by my office hours. Okay. Besides that, happy studying.